we'll go ahead and get started. And I normally don't use slides, but and in fact, the reason why I don't use slides is because I rarely make slides, and I generally much prefer to write on my little electronic whiteboard and things like that. But Dr. Tseng, another professor in our department, he taught this class last year, and he has his notes on this subject are just really good. In fact, better than my own. And so I was thinking, let's use Dr. Tseng's notes. And by having the slides, we can actually move a tiny bit faster. I like the slightly slowed down pace of writing on the whiteboard. That's my personal preference. But with Dr. Tseng's notes, so anyway, all credit to Dr. Michael Tseng, with whom I share my office. And anyway, so today we're going to cover composition methods. So we are still in the subject of generating random variables, okay? So again, we are saying with our computer and our pseudo-random number generator, we are able to produce random numbers from the uniform distribution only, okay? So that's the only distribution from which we can produce random numbers, but then we have a need for random normal numbers, we have a need for random exponential, a need for numbers coming from other probability distributions. And so how can we go from random uniform to random other distribution, right? And so we've talked about a few of these methods. One was the inverse CDF, okay? So if you are able to calculate the CDF, then all you have to do is you find the inverse of that thing, and you can get random values. And that's like an incredibly useful method for many things, okay? But in some cases, calculating the CDF directly is quite challenging. For example, the normal distribution, there's no closed form solution for the CDF. And so what can we do? We can we saw rejection sampling. Okay, so rejection sampling is another method that we can use to generate random values from another distribution. And today we'll take a look at composition methods. So again, the idea here is we're going to start off with random uniform, and based on random uniform, we can generate other things, and if we can generate other things, sometimes we can put those together to get other distributions. So, we saw that going from random uniform to random exponential is quite easy, right? And that was in your homework. You just do the CDF, which is going to be the exponential, and then the inverse of that's the log. It's quite easy, and so anyway, we'll just start off with some basic composition methods. Okay, so all right, I guess this is kind of just what I said. In addition to the inverse CDF, there's other methods, and these ones are going to be composition methods, okay? And so here are just some well-known compositions. These are kind of the definitions of the distributions themselves. So for example, if we are able to generate values from the standard normal distribution, if z can come from the normal distribution 0 to 1, and then we just square that value, then we have a chi-square distribution with 1 degree of freedom. This is kind of the definition that you should have learned in 100B, and it's a perfectly good way to get chi-squared values, okay? And then if you have two chi-squared random variables, so if you want more than 1 degree of freedom, what do you have to do? You just have to add a bunch of chi-squared distributions together, right? So you would add, so if V comes from a chi-square distribution with 1 degree of freedom, if you add random values of V together, you'd have more degrees of freedom. So anyway, if you have two chi-squared distributions, the first one comes from with m degrees of freedom, and the other comes with n degrees of freedom, then the ratio of those random values over their respective degrees of freedom will give you an F distribution. Where do we use the F distribution? In ANOVA, right? So when you are kind of calculating the ratio between your within groups, between groups degrees of freedom, or between one group and another group and things like that, when you're comparing the mean squared error, mean SSR divided by DF is mean squared, whatever. Yeah, mean squared for the between group. And you take that ratio versus the within group variation in ANOVA, the resulting value follows an F distribution, okay? And so you use the F distribution in ANOVA. And if you do this, then we have the T distribution, okay? So this is the normal kind of, and we divide by V, the chi-squared thing, to get a T distribution. T distribution kind of describes the sampling distribution of a sample mean, okay, where the population variance is unknown. All right, so these are just some, this is using just the definitions that we've learned from 100B, okay? All of these notes I'm gonna post online, so you don't have to like frantically copy all of this down. You're more than welcome to, but I'm not gonna give you like any like pop quizzes in the middle of our thing, okay? Okay, the next thing we'll talk about is the Box-Mueller transform, okay? This is a way for us to generate values from the normal distribution exactly, okay? So, we saw the rejection sampling method to get values from the random normal, but that involves some throwing away of values, okay? And so the Box-Mueller transform is another way to do it. This is an excellent way to get values from the random normal. It is still not the way that our computer does this, okay? Our computer actually, when you use R norm on your computer, it uses the inverse CDF, and it doesn't actually calculate the direct inverse CDF in a closed form solution, but it just has a way to calculate the inverse CDF, which is, and it's an approximation that's accurate up to 16 decimal places, okay? And so that's what it's doing. Inside your computer, it's using an inverse CDF using basically this approximation formula, and that works quickly. But the Box-Mueller transform is another great way. I guess I cover this topic because it's almost like required in any kind of Monte Carlo class, okay? The computer doesn't use it, and we would never actually do this by hand, but it's kind of like one of those topics where, at this point, maybe we cover it out of reverence for the topic. Perhaps in the future there'll be a day where we're just like, okay, yeah, Box-Mueller, nobody does that anymore, so we're gonna skip over it. I don't know. Okay, I feel like if somebody were to see the class and see that I didn't cover the Box-Mueller transform, they would question, what did you teach in your Monte Carlo class? So I feel like I'm required to cover this, even though on a practical level, it's not used in applications, and it's and we don't really do this by hand. But it covers some good concepts. The idea behind this is rather clever in terms of going from random uniform to random normal in a way that we don't actually even throw away any values, okay? So we're not doing rejection sampling, we're not throwing away any values. Every value that we throw in will eventually produce values from the normal distribution, okay? And the idea here is we're going to take a pair of random uniform values, and we will get back a pair of random normal values, okay? And so we're going to go for this by saying we are going to try to generate values from x and y. We're going to say x comes from the standard normal, y comes from the standard normal, okay? And so the PDF, if these are independent variables, the joint probability distribution is just the product of their respective probabilities, right? So the PDF of the joint distribution is just going to be the product of f of x times f of y. And so we just take the standard normal for x and we multiply that by the PDF of the standard normal for y. Okay, and so we have this, and when we multiply this together, we get 1 over 2 pi e raised to the negative x squared plus y squared over 2. Okay, so this is the joint distribution of x and y. And for the Box-Mueller, the kind of the brilliance of this is that we are going to take this thing and change to polar coordinates, okay? So if you remember, you guys covered polar coordinates in like pre-calc or calc or whatever it is, okay? And you have to say, all right, in polar coordinates, you can map everything on the same plane using a radius and an angle theta, right? And so to go from x and y, which is, you know, along the x-axis and the y-axis, we go to polar coordinates, and the way we switch is we say, okay, the relationship between x and r and theta is that x is r cos theta, y is r sine theta. And then the other, you know, the other relationship that, well, I mean, you can derive this is that x squared plus y squared equals r squared type of thing, right? Okay, and from multivariate calculus, do you remember how to do a change of variables? So generally, we dropped the integration signs, but a lot of times you will have a change of variables situation when you're kind of dealing with some kind of integral. And so you might think you can imagine having you know, a double integral over x and y. So an integral over x and an integral over y, going from negative infinity to positive infinity, negative infinity for y to positive infinity for y. Okay, and then we would be switching to a double integral over r and theta, except r goes from 0 to positive infinity and theta goes from 0 to 2 pi. Okay, so anyway, we would do a change of variables in from x and y to r and theta. So this is just coming from multivariable calculus. And do you guys remember the Jacobian, which is the determinant of kind of all of the derivatives with respect to each other? This is like bringing back tragic memories of like math 30 something, right? Okay, so anyway, or maybe you just remember when you go from, maybe the easy part, maybe you forgot about the Jacobian, but do you remember going from dx dy becomes r dr d theta? Does that sound? Yeah. Okay, so you might have remembered the end result, okay? I mean, that's basically what we have here, okay? Is that, all right, so, you know, the Jacobian, you take kind of the ratio, you know, you say dx dy over dr d theta, and this whole thing becomes the Jacobian, which is, you take all of these things, dx over dx dr, dy dr, dx d theta, dy d theta, and the relationship, you know, how does x change with respect to r? That changes via cosine theta. How does x change with respect to theta? And if you know, going back to this, right? How does x change with respect to theta? The derivative of that would be negative r sine theta. Okay, how does y change with respect to r? It's going to be sine theta, because that's just a constant. How does y change with respect to, what did I say? Y change with respect to r is sine theta. Y change with respect to theta is going to be r cos theta. Okay, so that's how we get it. And we do the determinant, so we do this times this minus this times this, and we get r cos squared plus r sine squared, and that just becomes r. All to say, well, it's not written out here, but basically dx dy becomes r dr d theta, right? So So f of xy, we have this becomes 1 over 2 pi e to the negative r squared over 2 times r. Okay, so this is doing the change of variables. Is that okay? Sorry, I don't mean to be bringing back bad memories here. Okay, and so yeah, again, here we have we've changed. So we got basically the f of x and y now expressed in terms of r and theta, and it becomes r dr d theta. And we're going to do another change of variables going from r to r squared, okay? So if we look at, what is dr squared, that's going to be 2r dr. And so if we want to swap out rdr, okay, rdr will become 1/2 dr squared. Okay, so doing another change of variables, we're going to go from rdr, and we're going to swap that out for 1/2 dr squared. Okay, this might feel like, why are you doing all of this? We'll arrive at the final solution at the end. Okay, so we have this, and okay, so we've gone from the function over x and y to the function of r over r and theta, and now we're going to the function over r squared and theta. Okay, and so when we switch out, do the change of variables, this part remains the same. The rdr d theta, the rdr becomes 1/2 dr squared d theta. Okay, and now that we have this, we can factor this out, and we have 1/2 e to the negative r squared over 2 dr squared. Okay, so you can just kind of think of this as kind of like a v or something. Okay, 1/2 e to the negative v over 2 dv or something like that. And then over here, we have 1 over 2 pi d theta. Okay, and so this factors into a PDF over the variable r squared and a PDF over the variable theta. Okay, so if over here we have just a constant 1 over 2 pi, that's equivalent to the PDF of the uniform distribution from 0 to 2 pi. Okay, and then over here, if we are just drawing r squared, the value r squared, if it's easier to just think of it as some variable v or something like that, this is equivalent, if you look at this, is the exponential distribution with lambda equal to 1/2, right? Because it's lambda e to the negative lambda x, lambda times x, and so that's what we have here. Okay, so r squared comes from an exponential distribution with lambda equal to 1/2, and because they are independent, we can just multiply those two together. So we have r squared is independent from theta. Is the math here okay? All right, so we're going from a change of variables from x and y using all of what we remember from multivariable calculus, and now we have expressed the same joint distribution of our joint distribution in terms of r and theta. Okay, and so instead of having x and y coming from two independent normal distributions, we have r and theta coming from a uniform and an exponential distribution. And these are easy to simulate values from. Okay, it's easy to get values from the random uniform. It's easy to get values from a random exponential. Okay, so we can get random values for theta and r squared. And if we can get random values for theta and r squared easily, then we can convert them back to x and y. Okay, and so the box Mueller transform is going to say get theta from random uniform 0 to 2 pi, get v from a random exponential, and you will get r by doing the square root of v. Okay, and then you just plug those values to get back x and y. X will be r times cosine theta, y will be r times sine of theta. Okay, where r and theta are the random values that you generated from these random distributions. Okay, so random uniform will be coming from 0 to 1, and then to go from a random uniform to the exponential, we just use the inverse CDF, and so we have the kind of the random value v is going to be -2 times log of u. Okay, so this is how we get random values for v. And so when we do this computationally, we're going to have if we're dealing directly with random uniform, okay, we can say theta comes from random uniform times 2 pi. So this will be random uniform from 0 to 2 pi. And then if v is coming from, or some letter comes from uniform 0, 1, we just plug that into -2 log v here, and we take the square root of that to get our radius, and we compute this. And so we go from 2 uniform values to 2 random normal values. Okay, so this is Box-Mueller. It's a very good algorithm. And so you might wonder, why doesn't the computer use this? And the reason is that calculating the cosine and the sine and the log is slightly computationally expensive. Like these are like the log is a transcendental function, and so we take for granted calculating the log on the computer is an easy thing to do, but the computer actually has to work a little bit hard to get you the log of some number. Okay. We don't think about it. We just say, computer, give me the log of this, and it does it. But it actually requires a little bit of hard work for the computer. Okay. Same thing with like taking the square root of something. Like if somebody asked you to take the square root of a value by hand, you would not be able to do it, right? I mean, there are ways to do it by hand, but we don't teach that anymore. Yeah, I don't know. I don't know when. Yeah, somewhere along the way, they used to teach taking square roots by hand, and we said, you know what? We know what a square root is. It's not necessary to learn how to do it by hand, and so we say, hey, just use the calculator. And so nobody knows how to do a square root by hand anymore, and maybe that's okay. I don't know. When the robot revolution happens, we might be in trouble. But same thing with calculating a log. All of this stuff. Okay. Anyway, so that's the Box-Mueller transform. Again, we don't do this on the computer, but it's rather a clever method, in my opinion, for getting this. Okay. So here we're going to just use random uniform values, okay, to get u and v, and we use those to get x and y, to get our random normals. Okay, so we're going to get two random normals, and we can plot this out, and there is your random normal distribution going bivariate random normal covering x and y. Okay, and I mean, if you just wanted one thing, you can just append x and y together, and you'll have standard normal random uniform, right? Okay. All right, any questions on this? We're all good here? Here, wait, let me go ahead and close down our poll here. Close poll. All right. I have my suspicions here. Well, we'll see how much time we've got at the end. So don't leave, all right? Just in case I do this. All right. Okay. So now we have a method for calculating random values from the standard normal. And yes, question.
For
You forgot to do the poll? Oh man. All right. How do I? I don't know if I know. I don't know if I can reopen the poll. Honestly. Huh?
Well, does that work?
Clone the poll. Oh, this is gonna. Oh. All right. All right. Okay.
We could just do roll call.
All right. Okay. Well, I want to cover a few more slides, and then we can do the actual roll call if we've got the time yet. Yes.
Is approximation versus CDF actually faster than sine?
Yeah. The method that the computer uses is used because it's fast, and I should probably look into how that inverse CDF thing is calculated. It's implemented in C code, and I'm sorry, I don't know the how it works. That's what the computer does, and but it's not. We like doing this Box-Mueller thing because we feel good about being clever. Because it is a clever method. It really is, but it's just not used.
A lot of transformations
Today, yeah. Okay, and then so going from standard normal to some other normal distribution. This is easy, right? We just basically use z-scores, so we just say multiply z by sigma and then add it to the mean, and then so when you do that, you get some other normal distribution with mean mu and variance sigma squared. Right? So I think this is something we're familiar with because in Stats 10 we always had to go from some other random normal to the standard normal by using the z-score formula, and basically if you want to go the other way, you just inverted that formula, and that's exactly what we have here. Okay. So now we have a way to generate values from random normal distributions, which is easy enough for us. Okay. And then we will talk about convolutions. This is just another way of describing random variables that consist of sums of other random variables. Okay. So if we've got a bunch of independent random variables, then you could have another value, s, which is just the sum of those random variables. Okay. And so this is how we get other things. So for example, so we looked at inverse CDF method for getting binomial, but you could also just do a whole bunch of random uniforms and have a cutoff point to turn the random uniform into a Bernoulli, right? So if you want to go from random uniform to a Bernoulli with probability parameter p, you just say, here's the cutoff. If the random uniform ends up lower than p, it's going to be 1. And if it's higher than p, it's going to be 0. Okay? So you just say, you do that. And then you will have some random variable, Bernoulli variable x, 0 or 1. And then if you repeat that m times, then the sum of those will be exactly the definition, by definition, what the binomial is. Okay? And but we covered doing inverse CDF for binomial, and that's probably just as effective. But whatever. Okay. I guess it's a question, how hard is it to get a random uniform? And so far, we never actually even covered the random uniform. I just made a little video clip. Not a video clip. I didn't make it. I linked one about pseudo-random number generators. Okay. Over here, you've got the Poisson distribution, and if you've got, one Poisson distribution, then you can have, another. So the sum of Poisson variables is another Poisson variable, okay? You've got geometric distributions, and then you get the negative binomial, all sorts of whatever. These are like your random variable definitions, right? all right, inevitably someone asks, what do we need to know for a test, right? I don't know, I'll try to decide. These are like a lot of definitions that probably I will not test you on. Maybe just some of the basic ones like the binomial and the chi-squared. I think these are probably good ones, okay? So the chi-squared, each variable z comes from the standard normal. You square each of those things, and when you sum up m chi-squared variables with 1 degree of freedom, you're going to get a chi-squared variable with m degrees of freedom. Okay. And then you've got the gamma distribution. Okay, all right. So blah, 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 right? And then, all of these things you can, so if you remember, all of your nightmares of 100B from how all of these different random variables are related to each other, we're basically going to use those definitions to get other random variables, okay? That's how these things work. Okay. Yeah, I would say these are good to know, but, are you going to be tested on this? Probably not, okay? Maybe I shouldn't paint myself into a corner like that. I would say know the chi-squared, know the binomial if you had to do it the way via convolutions, okay? Okay, and then lastly, we have mixtures of distributions, okay? So, mixtures, it's kind of like you got one normal distribution and then you got another normal distribution. And when you mix those together, you get something that looks like this, right? So if you have two normal distributions, so here we've got a standard normal, mean 0, standard deviation 1, and over here we've got another normal distribution with mean 3 and standard deviation 4. So actually, this is not what the picture looks like. We have each of these PDFs, and then we can combine them. And so in this case, the mixtures have equal probability, and so we would mix them with ratios 0.5 and 0.5. But that might not necessarily be the case. And so how can we sample from this mixture distribution? Okay. Well, rather than trying to find the CDF of this thing and inverting it, which is going to be like a almost impossible task, just use the idea of, randomly sample to decide whether you're going to come from distribution 1 or distribution 2, okay? So all you have to do is you just flip a coin here, or you just randomly sample uniform 0 to 1, and if it's less than 0.5, it's going to come from distribution 1. If it's greater than 0.5, it comes from distribution 2. And then if it does, just use the respective PDF, in this case being a normal distribution, to generate some value, okay? So here, it says first verify that this is a PDF, so we do some math and we go, oh yeah, it integrates to 1, so great. And then, and over on this side, to get this, we just generate a value k to decide whether it will come from distribution 1 or distribution 2. And then once you have which distribution it comes from, you generate a random value from that distribution. So here we could use Box-Mueller or whatever method it is to generate a random normal, and here just generate a random normal from a different thing there. Okay. And then if you have some more complicated mixture, like a mixture of m different components, which is entirely possible, then you do basically the same thing here. Okay, so you have a random uniform basically to decide which category it comes from, and once you have which category it comes from, then you use whatever method it is to generate a value from the respective random distribution, okay, whether it be a normal or an exponential or things like that. And so this allows you to generate values from some mixture things. So for example, you might say, if we were doing the heights of people, an approximate thing is we can say, some people are men and some people are women, and the heights of men follow this normal distribution and the heights of women follow this normal distribution. And depending on, where you are located, you might have different mixing proportions, right? So if it's just a large city, it's probably something around half, 50-50-ish, okay? But if you are at, if you're going to do heights in the military, okay, the military is probably like 85% male and 15% female or something like that, something around there. And you have to, do the mixtures appropriately, right? And that's the simplified version where we just consider male and female heights and not people who are non-binary. And if you are able to come up with some kind of distribution for people who don't fit either category, then you can include that in your mixture as well, and things like that. And so the respective distributions will be quite different here. Okay, I guess we've got a little bit of time, so I'll do an actual roll call, and we'll just see if everybody actually is here. So let me go ahead and stop our video here.